going to talk about next time is actually converting from one basis to another. All right, and so that's an important thing, and it's important really to understand what a basis is, intuitively, so that you can understand what it means to convert from one basis to another. Right, so that's what we're moving towards. Right, so that leaves you pretty much off the hook in terms of problems to do. So what that means is that you should really take the time to go back and just study what we were talking about tonight and just understand the vocabulary. The vocabulary is so very important. Right? So that next class, when I start talking about this, you can have a pretty good idea what I'm talking about. All right. It's not terribly difficult in terms of the process by which you convert from one set of coordinates to another, but it can be a little mind-bending when you consider the visual representation. So that's kind of why I'm here. The theorem itself, I mean, it's very linear algebra-esque. Beta is a set of vectors in the vector space V. Then for each x in V, there exists a unique set of scalars, C, such that a linear combination is formed. All right, so cool. If B belongs, beta is, again, a set of vectors that is a basis for V and x is a V, then the coordinates of x relative to the basis beta, or the beta coordinates of x, are the weights, C, that form that linear combination. Right? So really what it's just saying is when you have that relationship, that linear combination, part of that is going to be the vectors that make up your basis, and part of that is going to be the transformed coordinates. All right, so you're going to have a coordinate that you start with, or a set of coordinates that you start with, and a set of coordinates that you end with, and you'll have a transformation matrix, which really just ends up being your new set of bases. All right. So all of the above boil down to the following rule: x is equal to beta times matrix x sub beta, where beta is the coordinate matrix and x sub beta is the coordinate vector. All right. So, okay, cool. We do have to consider what on earth any of that means, aside from the linear combination part of it, which by now should be kind of like an old hat. You're pretty comfortable with that. But looking at this relationship, we could actually solve for really any component. If I wanted to, I could solve this for x sub beta. And that would be the inverse of beta multiplied by x. I could also solve it for beta, poor quality beta. A little too ostentatious. So we'd be looking at the inverse of x sub beta multiplied by x. The problem with this one is it doesn't always hold, all right? Because it might not be invertible, because we're talking about a vector, so there's only certain circumstances in which a vector is invertible, right? So that is not going to be necessarily always true. So mathematically it seems to be true, but not necessarily I'll say helpful. All right, just because of the constraints related to matrix multiplication. All right, so you use a different approach. So anyway, the examples here, I talk about, and we'll work on the skill, and then we'll get into why this stuff works the way it does, or how it works anyway. Find the vector x determined by the given coordinate vector x sub beta and the given basis beta. All right, so it's just plugging and chugging away. If I have these two pieces of information, all I got to do is multiply them, and I'll have what I need. So x is going to be equal to the product of beta and x sub beta which is 3, 2, -4, 1, multiplied by -2, 5, which really isn't that bad. So I'll just do it by hand because I think we actually have it figured out by hand before I'd even get my calculator, this information typed into the calculator. So we're looking at -6 plus -20, so -26, and then -4 plus 5, so that'll give me a 1. All right, so it's like, okay, so what is that? What does it mean? What does it represent? All right, so I'm gonna speak of it in everyday language, normal people speak, although it may not seem very normal after you see what I have to say. All right, so this matrix B is the new basis. All right, so the new, quote unquote, new basis. All right, ordinarily it would be 1, 0, 0, 1. Right, so usually it's the ij because we're in 2 space here. All right, so I, which is 1, 0, became 3, 2. J, which was 0, 1, became -4, 1. Right, so this is my new basis. I have a new system that's based off of these 2 vectors as they're defining attributes, I guess. Right, now this one, oh, and this is where it gets a little weird. Call this beta world. All right, so beta world. So this is a coordinate or a vector, but the vector is related to a coordinate. So I'll say coordinate in beta world. All right, and this -26, 1 corresponds to the coordinate in the real world. Right, specifically R2. All right, so it really is the real world, real space. All right, so you have a system that is defined based off of, well, overusing a term here, based off the bases, 3, 2, -4, 1. And so a coordinate in that universe, in that world, would correspond, if we were to just plot this coordinate under their rules, it would correspond to our coordinate of -26, 1. All right, in the way that we're used to plotting points. All right, so sometimes you're given the point in the real world and you want to know what it would be like in beta world. And sometimes, just like this one, you're given it in beta world and you want to know what it would be like in the real world. All right, so that's what we're up against in the second case. What I'm going to do is write the relationship, which is x of beta, so the coordinate in beta world, would be based off of the product of the inverse of beta and x. All right, so it's still really the same structure, except now we're applying an inverse. All right, so all right, so we're just going to run this calculation, but this time, it is worth our time to put it in the calculator because we know how troublesome it could be to come up with an inverse. All right, so I'm going to pop this in there. I may have actually already popped it in. Let me see. No. Looks like I popped the next one in there. Well, and that looks good. And then 2, 3. And then we're just running the calculation. So matrix A as an inverse times matrix B. And you get negative 8.5. All right, so in the previous example, what we kind of gathered from the operation is that multiplying a beta vector by the basis for beta converted it from beta world to the real world. So it makes sense that if I want to do the opposite, if I want to go from beta world, I have the x. If I want to go to real world back to beta world, I would just do the exact same thing but in reverse, right? So instead of multiplying, I would divide. The matrix method of division is multiplying by an inverse, right? So the exact opposite procedure, right? So this is what the coordinate would be in beta world, right? So we could play around with the graphs of these, and it's definitely worth a little bit of time to do that. So I'm just going to draw a quick sketch. Probably pretty poorly, but it'll be something. So again, beta world, real world. Ooh, little stray marks there. All right, so if I draw a sketch, plotting vector 2, 3 is going to be super easy, barely an inconvenience. I really love that channel. I have a line draw tool, I should use it. I have a line draw tool, I should use it correctly. And there it is. And not really. I don't know why I'm caring so much about the detail here. It's a freehand drawing for the most part. Anyway, all right, but anyway, that's 2, 3. All right, so specifically x. Now we have these basis vectors. -1, 1. I'm sorry, 1, -1, and 2, -1. So I'm gonna sketch those out too. There's no reason that should have happened. So here's one basis. And 2, -1. I really probably should have wrote that in another place. So let me put the 2 and the -1 here. And instead of actually labeling them with their numerical values, executive decision here, I'm just gonna call one of them B1 or lowercase b1, and the other one B2. All right, because the columns of the transformation matrix, because that's really what it is. I mean, when we were converting by by rotating coordinates and reflecting them, we were creating a matrix to multiply by a vector to transform it into another coordinate. But the reality is we were changing bases. And so what's actually happening, because it's kind of weird and cool at the same time, but what's happening is you're not really changing the vectors. You know, like when you multiply a vector by a matrix, you're actually not changing the vectors themselves. What you're doing is you're changing the scale around it. You know, you're changing, instead of going by I and j, you're going by b1 and b2. But it's kind of like the point is remaining fixed. It's just everything else is morphing into a different reality, right? So, I mean, you kind of see visual examples of that in movies and TV all the time, where the person, you know, like Star Trek was really, really big on this, but I'm sure there's other shows, like if something happened in the past, you know, like there's time travel involved, something happened in the past, they change the past, and then the person in the future change, you know, they're still in the position, but then you can kind of change you can see their reality changing around them. You know, that's really what's happening here, except not as interesting, I guess, because it's just multiplying matrices. But, you know, like that's the theoretical component of it, right? So what we're going to do here is think in terms of b1 and b2 as opposed to I and j. So instead of saying I have a coordinate 2, 3, that's 2 over 3 up, I now have a coordinate negative 8, 5. All right? Now that negative 8, 5, it is negative 8, 5. That negative 8, 5, I'll just kind of jot it off on the side here, or maybe below it. Yeah, below it. Is negative 8 b1 plus 5 b2. That's that linear combination we were talking about before, all right? Now, if your bases are 1, 0, 0, 1, then that's negative 8i plus 5j, but they're not. Our bases are whatever they were that plotted 1, negative 1, and 2, negative 1, or whatever it was, right? So what this is telling me is that I have to take negative 8 steps along b1 and then 5 steps along b2. And it's at this moment that I realized that maybe I didn't give myself enough room to do this, but I'm going to make it work. So 8 of these. So 1, we'll plot a point. 2, in the negative direction, so opposite of the positive direction. 3, 4. I'm going to end up overwriting stuff, but that's all right. 5, 6, 7, 8. All right. Now, I'm also going to move 5 steps in the direction of B2. All right. So I just have to ballpark what B2 looks like. All right. So I'm just going to take that. It's vector sums. So it's going right back to the beginning of the course. That's what B2 looks like roughly. I need 5 of those. 2, 3, 4, 5. Like I said, poor quality diagram. All right, but this would be my endpoint. All right, and that would correspond with a vector. All right, and so this would be, in theory, this should be 2, 3. All right, now if I put even a teensy tiny little bit of effort into creating a decent looking graph, you would see that. The best way to do it would be to do it on the same set of axes. All right, so you plot your 2, 3 with graph paper. because it actually is like the one situation where graph paper would be very helpful. And it's just, I haven't quite figured that out here. I know I can make the background into graph paper, but it'll make it for the entire notebook. And then when I try to take it back, it'll remove it for the entire notebook. So it's not quite there yet. But if you do it on graph paper, plot 2, 3, plot your B1, B2, and then count in terms of B1s and B2s, when you have your linear combination, these movements should map directly to the point 2, 3. All right? And so what ends up happening is, what people will do is actually redefine their x-axis to be one of the given vectors, the new bases. Right? So what you could actually do is make this a horizontal. Like if you really wanted to think in terms of B1 and B2 here, you wouldn't necessarily want to look at it this way, because your reality is in terms of verticals and horizontals. So just this is the truly mind-bending part. In another universe where this is the reality of it, right? B1 and B2 are your I and J. B1 looks just like I to them. B2 looks just like J to them. All right, their B1 is 1 unit movement along the horizontal axis. Their horizontal axis, B2, is 1 unit of movement along their vertical axis. Right? So when they actually plot points, their graphs would look like this. But to us, it looks like this. All right? So it is really just a matter of perspective, but it's a pretty intense way of looking at things. All right? So, and interesting. Hopefully. So I'll put stars on B and C. You don't have to create graphs for them, but I would encourage you to do it at least for one of them. Just to feel this out on your own. Look at this. Another way of saying x of beta would be the coordinate value of x relative to beta, right? But I look at that as a coordinate in beta world, all right? So I over example would be actually hitting the record button. So yeah, just raising a matrix to a power. If you had to do it by hand, there's rules for it and everything. I mean, we've learned matrix operations and how to raise a matrix to a power, but I mean, it's a whole lot easier if that matrix is in diagonalized form, meaning that the only entries, non-zero entries in the matrix are along the main diagonal, right? Then it's very easy to raise that matrix to a power. When you have a matrix that's not in diagonal form, it's a little bit more complicated. So if only we could come up with a method by which we could transform a matrix so that it only contains, so it's equivalent in value conceptually, but only contains entries along the main diagonal that are non-zero, right? And so we're going to get to that, and that's going to be in our discussion related to eigenvalues, right? So, so yeah, that was B, and C is asking us to do the same thing, but in 3 space, real space dimension 3. So, same structure. X sub beta 113 208 1 negative 1 3 inverted multiplied by 0 0 negative 2. So B1, B2, B3. All right. So this one, you might legitimately, in my opinion, question the need to convert the X, which is in real space dimension 3, to beta space, because it's 0 0 negative 2. I mean, there aren't too many vectors that are going to be much more convenient than that. It's a vector that's living on the z-axis. I mean, if I had to graph that, I could graph that just like that. It wouldn't take more than a heartbeat to do. right? But yeah, we're at the point where we're just trying to learn the skills. So really, there's no bad example. But the more you start to consider what it is that you're doing and why you're doing it, the more you start understanding when it's a good idea to do it and when it's not. And that's kind of the point. You know, you go through a problem, like if I presented you a problem like this on a test, you'd probably look at it, hopefully, at that point and say, why would I want to change it from 0, 0, -2? That's a nice vector, you know? I guess you couldn't think up a better example, so that's what we got to do. He must want an easy one to grade. That's the real answer, honestly. There's always that balancing act. I want you to demonstrate your knowledge while also giving me stuff that's easy for me to grade. All right? It's a win-win. Now this one, same computations in the calculator as the last one, so you start to rely on that repetition. All right? So 1, -1, 1 would be the result in beta space. All right, now, something to consider. I gave you a program called Markov. All right? In that program, there are matrix operations. All right? It relies on you having typed in matrices, and then it does the work for you. So my question to you would be, is there any reason why you couldn't create a new program yourself where you modify the one I gave you to do something like this for you? I don't see why not. All right, so if you go into program, now my setup is a little bit different from yours, but it's essentially the same stuff, because if you go to edit, you hit program, go to edit, and then select Markov, you could see the actual code that's in there. That part is not going to be any different whatsoever. It's just the keystrokes that I had to hit to get there. So there's some of it that's very specific to the Markov chain, but you can see here that I have A times B. That's just an operation of two matrices. All right? So what you could do is actually write a program using this as your format, just have it do inverse of A times B, and have it spit out your resulting vector. Right? So like it will do that work for you. And so the notation would be that you would want the reader to know, whoever's using your program, which in theory would be you and maybe like anybody you share the program with, to know what it is they're typing into A and B and why they're typing those values into A and B. All right? Now there is a way to, within the program, input values into a matrix. It's just too much of a pain to really bother with, because what happens is the user has to define the dimensions of the matrix, and then all that information has to get stored, and it's not as easy to store it within the function, the matrix, the program function is not as easy to store it into the matrix. So any of these matrix-related programs, it's much easier for you to actually have the matrices already put in, and then the results are determined by the program itself, right? So let's say you wanted to do this, which in most cases is something I would imagine you kind of want to do, right? So you would go to program, you would create a new program. So on your calculators, there's a column that says new. So you'd go to that new, mine is create new, and then you'd name it. You'd name it whatever you want, but what you could do is you can just call it change of coordinates, all right? So something simple like CHG coordinates, so COOR, if it lets you. I think you get up to 8 characters, all right? And I'll paste this program in there so you can actually see what I'm doing. You can put a description with this app. The problem is your calculators they're not, I mean, I'll call them space age because like that was the 60s, but not like 21st century. They're garbage. So anyway, this is what you have. So how would you put a description in there? Well, what you would do is you would actually have the program display a piece of information to the user. All right, so program, you would see that there's an input-output option. If you hit the right arrow, it's input-output, and then you just select display, DISP, and then you just display the information. All right, and for this particular program, generally you're selecting the program because you know what you want it to do for you, all right? But maybe you forgot, or maybe you have another program that's kind of similar and you're getting your wires crossed. So this is where you put a little reminder in for yourself. You open a set of quotes, so alpha plus brings up the quotes, and then you just type in some text. Like, this is to convert into beta space, or so keep it simple, converts into beta space. You just got to hunt for the values though. Speaks? No. Yeah, so you got to hunt in tech. So above the math, alpha math gives you the A, alpha apps gives you the B, alpha program gives you the C. So that part sucks. Mine's better, but you know, it is what it is. All right, converts to beta space, and then I would even include something like input matrices, or did you input matrices? If not, quit. You know, so must input matrices. Now, you might not think you need any of this, and if that's the case, then you're good, because you wouldn't have to type any of this. All you're going to do is recall the Markov program and just make adjustments to that, right? But I would put this stuff in here because honestly, I know myself, and I can see myself next semester teaching, you know, in this exact same moment saying, I got this great program that'll help you convert from beta space to real space, which is the exact opposite of what this program is going to do, right? So I will have forgotten what it's for, and I'll get the wrong answer, and everybody will laugh at me. I mean, I won't care about that because I have healthy self-esteem and ego. But it's part of the fun, I guess. So I need these little reminders. So that'll come up. When I run the program, that's the first thing that's going to come up. Be like, okay, this is what it's for. Oh, I didn't put my matrices in there, so I got to quit out of this program. All right, so let me just actually run this program. So if you're following along, by all means, continue to follow along. But don't quit out of this. Just leave it here. I just want to show you what would happen, because maybe you're not that familiar with this kind of stuff. So I'm going to execute the program. It's going to, I hit display. It said done, which is a bold-faced lie. Conversion. All right, well, in your calculators, it'll do it correctly. Mine is just being a jerk right now. But what it'll say is converts to beta space, must input matrices, right? And then what you'll say is, oh crap, I don't want that, and I didn't do any of that. So you hit on to interrupt it. It'll ask you if you want to go to an error or hit quit. So you select quit, and then you put your matrices in and you're good. All right, so I want to bring the Markov program in here so that I can just modify, because I don't want to reinvent the wheel. So second store brings up recall. And then I just tell the device what to recall. So I'd hit program and then select execute, or in the execute menu, which is the default menu, select Markov. And what'll happen on yours is it'll actually recall the entire program. For some reason, this is not quite exactly the same. So that's kind of annoying, but what I can do is show you a different, really want this to actually make sense. So we're going to have to slum it here and do it the old-fashioned way, which is, of course, use a screen record from my iPad onto this Explain Everything app. You know, like they used to do back in the 90s. All right, so program, new, I overshot the Mac. Core, CHG core. And then again, just a little memo to myself. So program, IO, display, alpha plus, the quotes are necessary. All right. Let's make this a little, and the contrast is a little off. All right, display, and then a little reminder. All right, convert. So second alpha locks your alpha. So CONVERTS. Space is the 0 button. 2, so TO, space again, beta, space, space. Need to input matrices. So I'll try to keep it simple because it's obviously harder to type here. Need input matrices. Close them up, and then hit enter. And then I'll show you what I was trying to show you before. If I run the program, so I quit out of here, program, change coordinates, hit enter, and it brings up the memo, all right? So program, edit, to continue working on it. If you want it to have a little bit more structure in terms of that memo, you have to write it in as different displays. So, because otherwise it'll like wrap into the next line. So what you could do is display converts, display to beta, display space, display, you know, like separate lines of code, right? I mean, it's annoying, but that's how it works. All right. So then now we do the recall and it's going to work. So second store, recall comes up at the bottom of the screen. Program, you go to execute, and I want my Markov program, and hit enter, and it recalls the entire Markov program. And so what I'm just going to do is just go and delete anything that I don't want. All right, so for example, I don't need a running counter. I mean, we haven't actually used the Markov program yet, so you don't know that you don't need a running counter, but we don't. So I'm going to hit clear on that, delete. I don't need to label, I don't need an anchor within the program. So clear, delete. What I do want to do is find the inverse of A. So I'm going to I'm just modifying this. So I'm going to hit insert, so second delete on B, and insert the inverse function. But I still want it to store in as a new matrix, right? Because when you write a program on these calculators, it'll just take that answer, store it into C, and unless you go to look at C, because remember, you're not actually going line by line through this code when you actually run the program. So for all you know, it's storing it in as matrix F. Like, how are you going to know where to look for it? What you wanted to do is be transparent. You wanted to display that result to you, all right? So display C, but as a fraction, because if it can be converted to fraction form, that's going to be preferred, right? Because you don't want an ugly decimal when you can have a nice clean fraction. All right, x plus 1 store x was just for the purpose of having that running counter that you'll see in the Markov chain program when we actually use it. So clear, delete, Lots of clear, because all this stuff is just related to Markov. All right. Now, if you want, at this point, you could make a notation to indicate to the user of the program that that this result is going to be a beta space coordinate. All right. So you could actually just say display. You could kind of sneak it in before this one. Display program IO. And, you know, just keep it simple. Beta space or beta coordinate. And then just make sure you close up your parens and you'll be in pretty good shape. Because it'll display that line, beta core, so beta coordinate, and then it'll display the matrix, matrix C, which would be a vector, in fraction form, which is precisely what we want. All right, so I can quit out of here. And so that quitting out is what stores your program. All right, so that's kind of, I guess it's good and bad at the same time. It's bad because that means that there's no reassurance of there being a save. So if you accidentally clear out a line of code, you've cleared it out. There's no undo. All right, but there's also the idea that if you quit out, you're not going to lose everything you just did for the last 10 minutes, like if you quit out a word without actually saving anything. All right, so I'm just going to put in my matrix. I'll do it for question B. So
Did you add a line to this part?
hit second delete, then hit enter. So I'll put in my 2x2. Now you may look at this as a program like, I don't need this program. I could easily multiply two matrices where one's the inverse. It's not really for that. It's more so in the event that you forget what you're supposed to do when you're changing coordinates. Like you forgot how to do it. Right? So not only do you have something in your calculator that's going to remind you how to do it, but you also have something in your calculator that will then do it for you. Because that's kind of a philosophical thing on my end. Not everybody agrees with it, but you know, I'm not oblivious to the fact that people store stuff into their calculators. You know, like formulas and, you know, like little notes to themselves, reminders, things like that, especially if it's a closed notes test. You know, I'm not going to sit here and take the time to wipe out everybody's calculators. But my philosophical choice is like, listen, you're going to do it right. You're going to put in a formula, make that formula do the math for you too. I don't like this nonsense where it's like, well, here's the quadratic formula because I can't remember it, so I'll just type it in as a program. Well, you damn well better make it do the quadratic formula for you too, because what the hell is the point if that's how it's going to be? All right. So this is along those lines. Right, so not only do you have a way of remembering your change of base technique, it's going to do the math for you too. All right, so I'd run my program, change coordinates. It'll tell me it's converting to beta, and look at that. That's exactly what it did. All right, so pretty nice. And of course, you can modify it in any way you want because it's your program now. But you can see how what we did was we took something that was in the Markov program that I gave you, and I just showed you how to modify it. And in fact, modifying it ended up being damn near deleting most of it, right? But you kept the important pieces, and that's all that matters. So you have a couple of programs now that you can work off of. I also threw a Pascal program into your calculators also. And that's so you don't get bogged down with expanding polynomials. Right, so Pascal's triangle. So if you had to take a binomial and raise it to like the seventh power or something like that, it'll give you all the coefficients. You get it very quickly. When that moment arrives, I'll talk you through that also. Where is it? It's like right. Yeah, we did a whole thing on it. 45 minutes or so. It's this, right? Just because I use betas here doesn't mean it's not true. Like whatever. This is some new space based off of this relationship. Right, but that space specifically is defined as real space. All right, so by multiplying a basis. All right, so now they're defining set beta as this, really it's a vector value situation here, but this is forming the base of polynomial space too. All right, so it's a little different now. But what we want to do is find the coordinate vector of P of t relative to beta. All right, so when we go back and we simplify the concept, maybe a little too much, but I do it for a purpose because I think it's kind of easier to keep track of it that way. All right, but polynomial space 2 is talking about a real space defined only in terms of polynomials with the highest power equal to 2. So highest power equal to 2. All right. So the way that would look in general terms you'd have, I mean, you could use any notation you want. I'll use typical polynomial or quadratic notation. So I'll say C BT AT squared. All right, so like AX squared plus BX plus C, just with T's instead. All right, that's the model for polynomial space 2. All right, so that works because then what that'll do is it'll define beta as 1, 0, negative 1, because I only really care about the coefficient. You know what? I'll actually write the variables in, and then we'll drop the variables. But for now, I'll just write them this way. So 0 t negative t. I'll write negative 1 t squared. 1 and then negative 1 t squared. And then 2, negative 1t, and then 1t squared. All right, so that forms my basis, but we're gonna drop the variables because all we need is the coefficients. Because as long as you know that the first entry, once you have the model that's telling us that the first entry is going to represent the constant term, the second entry is going to represent the power of 1 term, and the third entry is going to represent the power of 2 term, then you have everything you need. So this corresponds to a transformation matrix or the basis matrix: 1, 0, negative 1, 0, 1, negative 1, 2, negative 1, positive 1. All right, find the coordinate of vector P of t relative to B. All right, so they're telling us that x is equal to, and again, I'll write it with the variables, 1, 3t, negative 6t squared, which corresponds to just the vector 1, 3, negative 6. And we're looking for x sub beta. We're looking for the 1 in beta world. All right, and so based on what we covered on the previous page, it's not going to be difficult because we already did all the hard work. So, you know, and that was the setup. So x sub beta is going to be the inverse of 1, 0, negative 1, 0, 1, negative 1, 2, negative 1, 1, multiplied by 1, 3, negative 6. Okay, so that's calculator work. 1, 0, 2, 0, negative uno. Nope, 0, 1, negative uno. Negative 1, negative 1, positive 1. Double check. Looking good. 1 by 3 is what I want. Nope, 3 by 1. I don't know why I said 1 by 3. 1, 3, negative 6. That looks good. All right, so, oh, well, I could just repeat that calculation. So 3, 2, negative 1. All right, so these are the weights on my basis corresponding with the real point. All right, so the coordinate vector relative to beta. All right, so we'd be saying that this is the same. This leads us to 3 times beta 1, B1, sorry, plus 2 times B2, plus negative 1, so minus B3. All right, so again, this is my B1, B2, B3. Right, and it's something that you could verify. Put your weights in and simplify, and you'll see that it does play out. So, there's something to that. All right, but it's just a different application of the concept. Right, but and actually, I might as well just go through the little checkarooski here. So if I multiply by its corresponding weight, what I would do again, because these vectors strip down to their coefficients, they're wonderful, but I eventually want to have it back in polynomial form. So this would be 3 times 1, 0, negative t squared. Plus 2 times 0t negative t squared. And then minus 2 negative t squared. Yeah. All right, so if I run through the calculations here, 3 times 1 is 3. Well, the next part I could just kind of talk through. I don't think I need to write it all out. But 3 times 1 is 3. This is irrelevant. Minus 2 gives me the 1. 3 times 0, irrelevant. 2t plus t, 3t. Negative 3t squared minus 2t squared, so negative 5t squared minus another t squared gives me negative 6t squared. All right, so basically what we did was we came up with just now an effective way of representing a polynomial function in matrix vector form. So this is the same as saying P of t. All right, so that's a nice application of the concepts of change of basis, because really all we're doing is identifying what the appropriate bases would be and then going from there, right? So if I wanted to, I could even define it in terms of standard bases, right? But that could be a little iffy, because that would assume that a lot of things would be zeroing out, and also to assume that your coefficients are equal to all equal to 1. So if you did, what I'm getting at is if you did 1, 0, 0, 0, 0, 1, I'm sorry, 0, 1, 0, and then 0, 0, 1, you could define your vector, I'm sorry, your polynomial in terms of the standard unit vectors. But this does the job too, so you can go either way with it. Right. The benefit of doing something like this, even stripping it down so that the variables aren't there, is that now I can do calculus to it. All right, so I can apply derivative and antiderivative techniques because now I have a method by which I could represent a continuous function in vector matrix form. All right, so when we start talking about Jacobian determinants and things like that, we're going to start to see how we can apply the concept of a partial derivative to a vector matrix form of a polynomial function. All right, so number 2, I'll just put a star on because it's the same idea, except you're already given the polynomial vectors, and you're just looking for linear dependence versus independence. So that's not really anything new. The new concept here is being able to write your vectors appropriately. You're always going with the highest power. So in this case, the highest power is 3. So the little tip, well, it's not really a tip because it's flat out said or stated, but that defines what polynomial space you're working in, polynomial degree 3. All right, so even if that wasn't given there, you would still make that determination, right? Because there's nothing beyond the power of 3, but you couldn't stop at power of 2 because then you wouldn't have a way of representing the third power, all right? So our change of basis, just generalized. There's notation associated with it, but this is not really anything new. Like we just did this. It's just the idea that we're converting from one basis to another. I'm not overly in love with these formulas just because, I mean, just look at them. I feel like on the previous page, we kind of developed a reasonable way of conceptualizing this. And I feel like this goes kind of counter to that. It's basically saying, all right, all that stuff that you understood, I'm going to purposely try to make you not understand it anymore. Right? So feel free to not use these formulas because really the idea is that we're using a basis vector or a basis related to a vector, and we're converting from one form to another, right? So, yeah, it's really nothing more than that, all right? So, yeah, it's talking about those polynomial questions. Coordinate vectors to verify that the polynomials given are linearly dependent in polynomial space order 3, all right? So, just want to make a statement of what our bases are and then what the corresponding vectors would be. All right, so 2 minus t to the third power. Oh, I misjudged this situation. The moment has already arrived. Here we are. Insert video. A little on the small side. You know what I gotta, okay, I know what I gotta do. Undo, well. All right, so we have to expand out. The second polynomial is not bad, the 3 minus t squared. You don't need a program to do that for you. 2 minus t to the third, you borderline need a program. You really don't even need it for that, but you know, we have one, so why not use it? So program, go down to the one that says Pascal, which in theory for you isn't that far down. I got on a program writing kicks, so I have many. So Pascal, the binomial is being raised to the third power, but you can see the structure of what it's willing to accept. So A and B represent the coefficients, right? In this case, it's in terms of t, but that doesn't really matter. All we care about are the coefficients. So 2 and -1 will go in for A and B. So 2, -1 with a power of 3. And what that does is it gives you the binomial expansion of 2 minus t to the third power. Now, the reality is we're only looking for the coefficients when we write the matrix. So doesn't that mean we already have it? You know, so that's kind of the point, right? So with that in mind, maybe you do want to do it for 3 minus t squared because it's just going to do the work for you. So, you know, why not? But before you move on to that, you probably want to jot down this information. All right, so it's in the order of ascending exponents. All right, so if I were to distribute this out, we'd have the constant term first, then the power of 1, power of 2, power of 3. Right, so we have the structure of this. We know what polynomial space is supposed to look like. It's constant term all the way out to the highest order. All right, the next one is 3 minus t squared, so coefficient 3, -1, power of 2. All right, so 9, -6, and 1. And an understood 0 because if we're going up to powers of 3, and this one only expands out to a power of 2, it must be 0t cubed. All right? And the one after that is already taken care of, so we're done with the program. We could actually just kind of get to work now. All right? So, because the last one is 1, assuming I have my marker on. So 1, 6, -5, and 1. All right, so these are the columns that make up the basis of this polynomial space. We want to verify that they are linearly dependent. All right, so what that's telling us is that if we solve the homogeneous system related to this coefficient matrix, well, when you solve the homogeneous system, you're either going to get the trivial solution or not. If it's the trivial solution, then you're dealing with independence. You get anything other than that, most likely, because I suppose it is possible that you can get a finite solution, you're going to be looking at something that is, I think you are. So, 8910. I suppose we could put it, I'll put it as 3 by 4, leaving that column of zeros, just so I don't forget. But definitely at the point where we're spoiled enough to be like, man, I gotta type another matrix in. Still, again, I remind you, you don't have to do it by hand. It's 4 by 4, not 3 by 4. Even better. Double check Aruski here. Does not look like I screwed it up, which is definitely a win. Suspicious. Atypical. Completely out of the ordinary. All right, so 1, 0, -1, 0, 1, 1, and everything else are zeros. So I could just backfill all the zeros in here. All right, so I'm going to write out our solution just to really indicate what's going on here. Actually, no, I think we're good enough. I was going to say we could write out the complete solution, but we have our answer. Really, there's two free variables. I think it would just be kind of like extra work for the sake of extra work to write out the complete solution. So, therefore, linearly dependent solution, not just the trivial case.
Let's see your matrix.
Matrix A, you got it. An 8910, negative 12, negative 660. Yeah? Okay. All right, now the interpretation of that is really interesting, I would say. Now, what we're really getting at it, I mean, we're looking at three distinct vectors. All right, now if those three distinct vectors were going to span out all of polynomial space order 3, then what I would have, or what I would need, would be really 3 basis vectors. Right? I don't have 3 basis vectors. Right? Since I have 2 pivot values, I'm really only looking at 2 basis vectors. All right? So if you're looking at, again, the column space versus the null space, the column space are the first 2 vectors. The null space is anything that's not a column space. All right? And so if I were going to span out all of 3 space, I would need 3 basis vectors. So that means that, yeah, I can get some of polynomial space order 3 spanned out by the 2 basis vectors, but I'm not going to be able to get all of it, all right? Which is a problem because that's telling me that I would not, using these, if I'm calling these basis vectors, if I were to tell somebody, I have 3 vectors that you could define as the basis for polynomial space order 3, they would say, well, no, they're not, because I can't define every other polynomial in terms of these 3 polynomials. I could not write a brand new polynomial using these as the weights of a linear combination, right? Or weights imposed upon these vectors to form a linear combination to give me that brand new polynomial that would be represented in vector form, right? And, you know, I mean, how does that play out? Yeah, my suspicion is probably that it's the 3 minus t squared that would cause it to fall flat. I mean, because again, this is a row reduction. Things got simplified and reduced, you know. So you could look at this and say, well, that's the basis vector, but maybe it's the presence of that one instead of another one that might have been more encompassing that would have gotten the job done. Or maybe any 2 out of these 3 would have got the job done. You just need a 3rd one. All right, so these are some things that come into play. All right, but it's definitely, it's always coming back to the idea that we're trying to define any, whatever it is, any vector, in this case polynomial based on whatever you're given in terms of the vectors that are provided within the coefficient matrix. Good question?
Yes. I was just wondering, I think I might have missed it. Where'd you get the 8, negative 12, 6, negative 1? Was that the beta program?
No, the Pascal program.
Again, the Pascal.
Yeah. Right. So that, I mean, honestly, I just didn't want people to get bogged down with the ordinary algebra. You know, and also having this Pascal program allows us to have a little fun with this. You know, now if I gave you a problem on a test where it's to the 4th power to the 5th power, it's no more challenging. It won't be intimidating because you have the Pascal program that's going to get you those coefficients, right? So it's just I want us to be able to explore more complicated polynomials without having that oh shit factor of like, I gotta distribute all this out, you know, like we don't have to deal with that. All right, and so that's really what this is all about. Yeah. Back, it's by to the rule on the previous, I think it's previous page, yeah. All you have to do, and this is the foundation of the coordinate system, is all you have to do is take the vector that lives in a particular space and multiply it by that transformation matrix. All right, so I have a vector that's living in B space and I want to go to C space, multiply it by the vector that transforms from B to C. All right? So general procedure for converting from one form to another. You know, it still relies on a notation, but the idea is that you're converting from one basis to another. What we do is we're actually just really applying the same idea that we did when we were finding inverses. Right? So we're looking to get the identity matrix, form the n by 2n augmented matrix, and then transform this augmented matrix into reduced row echelon matrix. All right, so it'll look like this. The matrix to the right side of the reduced row echelon form is the transformation matrix getting you from one basis to another. All right, so that's how you convert from one, well, at least that's how you come up with the multiplier that allows you to go from one basis to another. Because the one challenge that we had was we were working with the standard unit vectors and going back and forth from that to our transformed, our beta world, right? But what if we're dealing with two worlds that are not the real world, right? So if we have beta world and delta world, for example, how do we convert back and forth between those two? Well, the two possibilities, one, use the real world as a way station. Convert, if I'm going from B to C, beta world to, say gamma world, beta world to gamma world, I can go from beta world to real world and then real world to gamma world. This technique kind of streamlines the process and allows you to come up with one matrix that'll get you from those two realities directly. All right, so I'll just take you through an example for that so you can see what the hell I'm talking about. But this right here, what we're trying to transform into is the I anyway, that's the real world. That's our standard unit vectors, right? This is the combined matrix that has the attributes of both B and C, right? So what we're just trying to do is take those two independent matrices and pare them down so that they're basically put into one matrix, all right? So that's a poor quality color. So this is B to C. Use colon. All right, so this is what we'll just put it in our calculators. Because like I said a few minutes ago, this is the same as saying, you know, like I want to find the inverse of a function, inverse of a matrix. I would be using the same skills essentially here. So I don't feel the need to assess you on that a second time.
Question.
Yeah.
Isn't it P from C to B?
Oh, Christ. Thank you. this over. Hmm, 2 and a 1. Okay. So then I just want to do a quick ref. On A. And we get that. Yeah, so that makes this a typo. That should be C to P. All right, so what this will give us is a matrix that we could use to transform any coordinate that's given in C world into a coordinate that's in B world, all right, or beta world if you want. All right, and so the other way around is just a matter of swapping columns. All right, so the first 2 columns get swapped with the last 2 columns. All right, so that part's not too bad. Yeah, I think the hardest part about that is actually just physically writing it. Yeah, I'm pretty sure. Yeah, they have row swaps, but I don't think they have column swaps. That would have been nice, but alas. I mean, in the end, it's only a 2x4, so you just retype. Okay, I think I got that. And so we end up with that matrix. All right, and again, that's the matrix that will allow you to convert a B coordinate into a C coordinate. All right, so that's really all there is to it because it's very procedural. It's also worth the time to actually perform some transformations and just kind of get a feel for it. But you know, obviously, you don't want to do that for every problem because that one graph I created, what was it, 2 pages ago, 1 page ago, it took long enough that if you had to do it for every single question, it would be kind of nightmarish. But what you can do is even take one of your basis values and convert that over and see what that gives you. Take an arbitrary coordinate, convert that over, see what it gives you. But ultimately, procedurally, there's really not much of a way you could screw this up, right? So as long as you know that you're taking the 2 matrices and putting them together and then running an ref on it, the only way that you can mess this up would be to zig when you're supposed to zag. You know, like you just did it backwards. And even that on a test, like -1 point. You know, so like I said, there's really no way to screw it up. And you could even see, I screwed it up. And the worst part is, it was right there. Like, I would imagine that at some point I was copying and pasting. I just copied and pasted the wrong thing. I don't know. I can't get out of my own way sometimes. Sometimes I don't even want to. All right, so put a star on the next one. And then we move. So then the good stuff. So what I wanted to do, I kind of teased this last time, is I wanted to take you through an example where, because you know the process of finding the conversion from one space to another, you know, like if you're going from Bob space to Charlie space, you know, like what would a B space to C space, it doesn't matter what they're called, beta space to gamma space. The process is not hard, but I wanted to show you just kind of like what you're saving yourself from. So I figured a quick small example probably wouldn't be the worst idea in the world. I'll just take what I did with number 3 and just kind of off on the side chuck this in here. I would even say that I'll take it as a typo. So I'm just going to make an example where we have x, because we're calling it b and c here. Instead of saying x sub beta, I'm going to say x sub b. And I'm going to define that as some vector 2, 3. Try to keep it simple, you know. Simple, but not too simple, like 1, 0, and stuff like that. All right. So I want to convert from B space to C space based off of the information in this, whatever it was, number 3, did I say? Number 3. All right. So the way you would have to do it if you didn't have this technique would be convert to real space. Okay, and we have a skill for that. You know, it's just on basis, you're converting it into real space. All right, so x would be b multiplied by x sub b. All right, so my b here has the columns of -1, 8, 1, -7. My thickness is off here a little bit, so. I already forgot the other one. -1, 8, and then 1, -7. All right, so that's the B1 and B2. All right, so I'd just be multiplying that by the value that I know is 2, 3. That was given. All right, that's going to give me the real space value. So just a quick calculation. It's going to be like a rampant set of requests for linear algebra students to all have TAs so that they could just type it in for you. I need an assistant. Why? Stuff's getting out of hand. All right, so it's just a simple A times B. Except you want to do it in the right place. So second means times B. So I get a 1, -5. All right, so that's the real space version of 2, 3, right? Based off of the information that we were given, and again, it's the weirdest thing to think of, but what you would want to do in order to visualize this, and this is the mind-bending stuff, in your ordinary XY coordinate system, you would plot -1, 8. That's your I. 1, -7, that's your J. This is telling you to take 2 of those -1, 8s and 3 of those 1, -7s, add them together, and that location that you get would correspond to, in real space, 1, -5. All right. So it's kind of weird to think about it, but if you conceptualize it into terms that you already know, like inches and centimeters, right? Somebody tells me that I have 12 inches, and somebody else is working with the metric system. So I show you, okay, 12 inches puts you right here. All they're doing is using their units to say, okay, well that means, what was it, 25, 27 centimeters, something like that. It was like 2.5, so like 30 centimeters, right? Something in that neighborhood. All right, that's all it's saying, except, this is a lot more abstract. But if you kind of ground it in stuff that you're more familiar with, then that'll make things a little bit easier. Currency exchange works the same way. All right. Actually, that's even more involved because you have multiple currencies interacting all at the same time. All right, so then what we want to do is convert, because we know that we can convert from real space to any other space. All right, so we want to convert that x value into C space. All right, so convert to C space. Now, ordinarily, the formula would be x equals C times x sub C. But I want an answer that is the vector in C space. All right, so x sub C would be equal to the inverse of my basis C multiplied by x. All right, so we know our x is 1, -5. C, the inverse, the calculator is going to figure that out, but it's 1, 1, 2, 1. But I want an inverse. All right, so, oh, sorry, before I forget, we have this 1, -5. I don't want to retype that just to, because I'm going to multiply by that value. So what you could do is store that in as matrix B, so you don't have to go in and retype it. All right, so one less thing to worry about. So the store key right above on, STO with the sideways arrow, and then call up matrix B. Now when if you were to go into matrix B, it would have the 1, -5 there. All right, so edit matrix A only, 1, 1, 2, 1. Quit out of there. I'm going to recall the previous calculation and just slip in an inverse symbol. All right, instead of the multiplication. All right, it just saved me the work. Hit enter, I get -6, 7. All right, so all of that was for the purpose of seeing what a B coordinate, which normally we would call a beta coordinate, would look like in C world. Without going to the real world, if we could have, we have Earth 1, which is here, we got Earth 2 and Earth 38, right? Instead of going from Earth 2 to Earth 1 to Earth 38, maybe it's Earth 2 to Earth 38, all right? Bypass the Earth 1, that's what this rule is going to do for us. So let's see if that happens, all right? So I want a rule that's going to convert from B coordinates to C coordinates, which is the one that I have highlighted right here on the screen. So we're looking at a big old OR. And now we have all that information there. So x sub C would be equal to that matrix multiplied by 2, 3. All right, this is my P going from B to C, and this is my x sub B. Say it again. Where did I get the what?
The 2, 3.
Oh, the 2, 3 is the original problem I made up. All right, so then we could just do it real quick. And type in my 2, 3, and it's still A times B, still the same computation, but this time you get to the negative 6, 7 in one crisp, clean maneuver. All right, now, depending on where you're sitting, this may be a better way to do it than this, because you look at it and say, well, I had to come up with the 2 transformation matrices to begin with, which means I had to put in the 4x8 matrix that told me P from B to C in order to do the multiplication. And so one might say, well, how is that any different from doing a multiplication, rejiggering it around a little bit to do a multiplication again? You know, if you're starting from scratch, you might look at it and say, well, it's all 6 of one, half a dozen of the other. It's the same amount of work, right? But if the question's just asking you to find the transformation matrix, then obviously you would want to use this technique, all right? So, you know, with that in mind, it's not difficult. It's just, you know, either way, it's very notation heavy, and keeping that notation organized is really the key to everything. All right. So, yeah. Anyway, so I got a little sidetracked with that and the other video with the program stuff. I don't think we're going to get to eigenvalues and vectors tonight, but that's okay. We're actually in this course. We're actually kind of ahead of schedule, which is surprising because I'm almost always behind schedule. So it's kind of a happy outcome. But for the next one, what I want to do is I'm just following the process. I want to figure out what the transformation matrix would be to get from B to C, and then also C to B. All right. The easier way to set it up would be to find the C to B first, just because of the way the information is presented. Really kind of steers you in that direction. All right, so what I'm going to do here is I'm just use a little shorthand notation, because I don't really want to write all this again, but P from C to B is going to be the B1, 2, 3 columns, followed by the C1, 2, 3 columns. All right, because it's all written there for us in you know, plain notation there, so it's really not bad. I just got blown up here. Oh, that's good to know. I don't know what that means. So, matrix, edit. This is going to be a 3x6. And we just got to put all this crap in there. So 2, 1, 1, 6, 4, 5, 0, 2, 1, 3, negative 1, 5, 101. 3, 3, 2. All right, so double check in. All right. So then, just row reducing. Matrix A, not the sign, not the inverse sign. Matrix A. And so we get that, which is beautiful. All right, so the transformation matrix from C to B is going to be equal to 2, 1, 1, 2, 2, 1, 1, negative 1, 2, 1, 1, 1. Now, if only this were a 2 by 2 matrix, we could easily figure out what the transformation matrix would be that would get us from B to C. All right, because if you kind of go back here, look, you see that the diagonal down values were swapped and the diagonal up values were negated. Right? That's part of the process of finding the inverse, the shortcut rule for finding the inverse. The determinant, 9 times 9 is 81, 10 times 8 is 80. Right? So 81 minus 80 is 1. The determinant is 1. The process for finding an inverse is 1 over the determinant, swap the downward diagonals, negate the upward diagonals. Bottom line, long story short, blah, blah, blah. This is the inverse of that. All right? So if you know one of them, all you have to do is invert it and you have the other. You don't have to reinvent the wheel. All right? So what I can do is just shorten up my matrix here in matrix A, make it a 3 by 3. All right, it'll truncate it, but the problem is it doesn't always, I mean, it definitely doesn't truncate it in the way that you want it to. All right, so adjustments need to be made, because what it does is it chops off generally the last 3 and leaves you with the first 3 in most cases, but sometimes it just picks and chooses what it wants to leave you, so that's kind of annoying. So you just make your adjustments. But the bottom line is you're making the adjustments from a 3 by 6 into a 3 by 3. So it's definitely a win. Right? So you have what you need. And now we're just going to invert this matrix. Math, bracket, math, enter, enter. And so we have the other matrix, the one that would get you from B to C. So from B world to C world. That's kind of funny. For the sake of brevity, you may consider writing a nice 1/2 in front of the matrix in terms of a scalar multiplier. And then just put your numerators in. You know, well, the bottom row would be impacted, but it might be a little nicer that way. But, you know, it's not too crazy. And so, a lot easier once you already have one direction. You just have to invert it to find the other. And you know, honestly, common sense might have got you there anyway, because when you do an opposite operation, that is what an inverse is. And so, you know, if you were taking a shot in the dark, if I told you on a test the transformation matrix going from C to B is this, what is the transformation matrix going the other way, then, you know, like you're probably going to guess inverse. Sounds like a great idea for a test problem. Put on test.
This problem?
Not the exact same problem, but what I was just saying of like if I give you a transformation matrix going in one direction, I just say, well, what's the transformation matrix in the other direction? Yeah, but I got to take these opportunities to remind myself, because if apparently recently I've been making, my mouth has been making checks that my body not cashing. And be like, oh, this will definitely be on the test, and then the test comes around and it's not on there. They're like, what the hell, man? I thought you said it was going to be on the test. To a concept called the Markov chain. Okay, so Markov chains, how to do it, for all that stuff. A vector with non-negative entries that add to one is known as a probability vector. A stochastic matrix is a square matrix whose columns are probability vectors. Right, but the term stochastic, just because people who write stuff for a living tend to write this stuff a little bit better than I do. So I just did a quick Google search on stochastic models, and really, it's just, very simply put, a stochastic model represents a situation where uncertainty is present. In other words, it's a model for a process that has some kind of randomness, right? So basically, I've always known of stochastic models as probability models, right? They involve probability in some capacity, right? That's the randomness component. And so it would make sense that the columns, if we're going, in this course, we're talking about the columns of a matrix representing vectors. And if a stochastic model is talking about probability, and the columns for us typically have represented vectors, then it would make sense that we'd be looking at probability vectors, right? A sequence of probability vectors together with a stochastic model P such that x of 1 is equal to P x of O, x of 2 is equal to P x of 1, and so on. You're calling upon prior information, so what we're looking at is a recursive model, right? So it's just calling on a previous calculation to get you a new calculation, all right? Also known as an iterative process, but you can probably see why I don't like saying that one too much, all right? So recursive is probably a little bit better. Although iterative tells you a little bit more about what it is, because iterate or reiterate, you kind of know what you're talking about there, because that's a word that you use in everyday language. Maybe not iteration, but definitely reiterate. So just carrying out a process over and over and over again. But the concept of an iteration is that you're taking a previous calculation and using it in the same model to generate a new result, right? And you do that over and over again until you settle in on what the true outcome is, all right? So it's pretty weird, but also pretty interesting, all right? Markov chain is described by the first order difference equation, all right? So x sub k plus 1 is equal to p times x sub k. Right, for k is equal to 1, 0, 1, 2, and so on. Right, so that's really just the same thing, except we've generalized it. We're saying that we're getting a result that is one further calculation down the line than what we started with. All right, just be careful. First order blank equation. It's kind of hard not in your mind to fill that blank with differential equation. They're not the same thing. All right, difference equation. We'll talk about differential equations before this is all over, but oh, looks like I updated the word problem. Look at that. I just switched back to FiOS again this past weekend. I think I'm going to probably switch back again, because it's just aggravating. Like, the remote works a lot better for FiOS, but the price difference, I don't know. It's like when they came to the door, they gave me a quote of $137 a month. And then I got the notice that says the bill is going to be $157 a month. And they wrote down, like they itemized it. So that 137 included taxes and all the government fees and stuff like that. But I think somewhere along the line something got screwed up. But the reason that's a problem is because my Altus 1, the optimum bill was like 161 per month. So 157 versus 161, that's not a significant difference. Except we have HBO with Altus and we don't have HBO with Fios. Right? So there's a lot of things going on. And actually a lot more channels with Altus.
If you call Verizon, they'll bring their price down to at least 135.
Yeah, and I'm still within the 30-day grace period, so if I threaten to cancel, then
They'll-
yeah,
they'll
they're
change
gonna
the
roll
price.
over. They're gonna roll over like a sick puppy.
They might even bring it down to 125.
They'll bring it down to free. That's what I want. Yeah, so we'll see. But I'm a procrastinator when it comes to that. I'd be like, yeah, I'll do it, and then I won't. So I don't know. All right, anyway, we got two competing companies, A and B, for example, Altus One and Verizon. After 1 year, some customers will keep using the same product, but some will switch to using the other product. The proportion of customers who keep using the same product or switch to use the other product after 1 year is summarized in the following table. All right? Suppose 3/5 of the customers use product A, and the other 2/5 of customers use product B in the beginning. Then we want to know what is the distribution of customers who kept and switched their services after 1 year. All right? So it's very simple because we have a matrix that's given to us, and it's a probability matrix. The columns have to add to 1. Check. All right, so if I just add up my first column, 1/4 plus 3/4 gives me 1, same deal with the second column. So P, my probability matrix, is going to be 1/4 and 3/4. For the first column, anyway. Second column, 1/3, 2/3. All right. Now, what we have here for that 3/5 and 2/5, we have a vector that's known as the initial vector. All right. So my initial vector XO. I mean, reality is it's just a vector. The fact, initial or otherwise, is determined based off of the subscript. If the subscript is 0, then it's initial. Right? So you can call it an initial vector, or you just call it a vector. It doesn't make a difference. But what we're after is known as a steady state vector. All right? That's the vector that would exist if you were to continue the iterative process in perpetuity. Right? So you were to go on forever and ever again, multiplying, taking the result and continuously multiplying it. What vector would you eventually settle in on? Right? That's what's known as a steady state vector. All right? And the Markov chain process gets us to that. Right? So what we'll figure out is, based off of these characteristics, what the long-term proportions are going to be. In the long run, what percent of the population is going to end up with Fios, and what percent of the population will end up with Altus. All right. So I want to find x(1). Well, or at least part A is only asking me for that. All right. So x(1) would be equal to P times x(O). All right, so then what I have to do is carry out this multiplication, which seems fun. Put it in the calculator. It's not too bad. So I'll do a 2 by 2. I'll put them in as, well, I'll put them as fractions. 1/4, 1/3. Automatically puts it in decimal. 3/4, 2/3, then matrix B 2/1, 3/5, 2/5. All right, so all I'm doing is A times B. Ah, I hit the wrong thing. All right, and so we have a transformation matrix and we have a vector. Right, this is the basis, and so that's the whole thing. We're really still applying the concept of change of basis, right? Or at least coordinate systems. It's contextual, so it doesn't feel like we are. But instead of having 1, 0, 0, 1, our new reality is in probability world, where the basis of vector 1 is 1/4, 3/4 rather than 1, 0. Right, so it's the same but different. All right, so we carry out that multiplication and we get this result. All right, but the issue is I now have to, so I can write that down. I'll just put an approximation, but I now have to use that number again for the second part. So 0.283 repeated and 0.716 also repeated. All right. So the way the vectors are set up, it's keep then switch. All right. So what happened is, and again, keep and switch. It's relative to where you started. All right. So we have an increase in folks that are keeping their service, and we have a decrease in those that are switching. All right. At least after 1 year. So what I would do at this point, in order to find the distribution that kept and switched after 2 years, same calculation, roughly, but this time it's x of 2 is equal to p times x of 1. So I still have my probability matrix, 1/4, 3/4, 1/3, 2/3, but this time it's, instead of being multiplied by 3/5, 2/5, it's going to be multiplied by 0.283 and 0.716.
You said keep and switch or keep or switch?
Keep, switch. First entry is keep, second entry is switch. Oh, and I think I said it increased and decreased. It decreased and increased. So the percent that are keeping their service has gone down, and the percent that is switching their service has gone up, because the initial vector was 60%, 40%. Now, after 1 year, based off of the probability matrix, we're looking at roughly 30% and 70%. Right? So it's a drastic shift in the opposite direction. Right? I said that backwards a few minutes ago. All right. So anyway, I have to multiply this matrix by this vector. Right? I don't want to have to type that in to matrix B. So what I'll do is I'll store it in as matrix B. So store, call up matrix B and hit enter. So now anytime I use matrix B, it's this matrix. All right, matrix A is my probability matrix. Matrix B is this new matrix. This new vector. So now when I carry out the multiplication, A times B, well, I don't really have to do anything new. All right, just by storing it, I'm able to let the calculator do the heavy lifting. All right, so we're looking at about 0.3097, 0.6903. So yeah, That's after 2 years. Now, for C, it appears C is missing a question mark. What is the distribution if the market is said to be stable? The distribution of the market would be constant forever, right? So what that's telling us is to find what's known as a steady state vector, right? So we carry out this operation repeatedly. Eventually it's going to settle onto a distribution, right? These numbers are fluctuating, but eventually they'll stop fluctuating. They'll settle onto a particular value, and then once they do, that'll be your steady state vector. All right, so for C, we're going to find the steady state vector. All right, so what that means is store this value, or this array of values, into matrix B. And actually, I mean, you could just do a little recall, second enter, do that. Recall, oh, get out of here. Recall, multiply. And you can see there isn't much difference between these two values, but there is a difference, so we do it again. So store, multiply, and we keep going until there's no change. All right, so there's slight change, and we're pretty confident that we know what the steady state vector is going to be. It looks like it's going to be about 0.3 and 0.7, but about really isn't good enough. I want to know what it's going to be exactly. So I do it again. Even less change, but I want no change. All right, very, very close. Yeah, one more time. One more time. Oh, so close. One more time. One more time. So close, it's probably, as you said, one more time. And there it is. All right, so no change in my vectors. So this is my steady state vector. This is what we could expect our long-term vector to be. All right, so in the long run, we could expect roughly.
Oh, it's such a pretty fraction.
Oh, it is? Should have investigated that. Let me do that now. Some math. Oh, jeez. I don't need to do a screenshot on this. I just write that.
I mean, the original fractions were not as pretty, but they were round.
Right.
They got
Right, so 4/13 of the population, which amounts to about 31%, is going to keep their service. About 70% or 9/13 of the population is going to change their service. All right. So, yeah, you kind of look at it in the context of the real world and say, wait a minute, what happened here? Because in the first year, or after the first year, sorry, we had 60% of the people keeping their service and 40% of the people changing their service. And then it turns out that over the long haul, it's gonna be a complete role reversal where most people are switching their service and a smaller minority of people are keeping their service. And then you think about the reality of the situation, like FiOS has 2-year contracts, right? Altus doesn't, but maybe there's a promotional period between the first and second year that expires. Maybe you had, I definitely had free HBO, Showtime, a couple of things for the first year, and then it went away. So at that point, you start thinking, okay, maybe I'll switch, right? But odds are, you know, you get 1 year in, you're not looking to switch because you're still getting all the incentives for having already switched to that program, right? So, you know, like the physical, or not physical, but the realistic contextual aspects of this could explain why there's such a change from the 60% to the roughly 30%, right? But mathematically, this is the process. Now you might say, well, that's a hell of a process because, you know, like how many iterations did it take to get there? Like, holy moly, look at this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Honestly, I don't even know if I'm counting it right because no, one of them is storing. So I'll cut this in half, but I'll get a reasonable estimate. 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So we're talking about like 10 iterations, really, because part of that process is me just storing the value. All right, so it took really 10 years to see what the stabilized market would look like. All right. What if it was 100 years? What if it was, what if it was anything more than 10? I mean, that's really what it comes down to. So it's like there's got to be a better way to do this. Well, I'll find out in a second if I've already done this. In your calculators, just hit program. Do you have one that says Markov? Damn it. All right, well, it must have been the other class I did it for. So, yeah, because usually in the beginning of the course, I dumped the necessary programs in. But what I did was I wrote a program for the Markov chains that will do these calculations for you. It's just you have to, I mean, you obviously have to type in your initial vector and your probability matrix, but then it's programmed to do the iterations for you. So you just hit enter, 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 as opposed to store, recalculate, enter, store, recalculate, enter, and so on. So what I'll do is while you're taking the quiz, I'll dump those programs on your calculators so that we can use time effectively, I guess. All right, but it's pretty basic. All right, the weather in East Bend is either cloudy, rainy, or sunny. The weather on one day is affected by the weather the day before, but not by the weather on earlier days. In fact, we have the following probabilities. Table of probabilities for tomorrow's weather. All right, so you have cloudy, rainy, or sunny today, leading to possibilities of cloudy, rainy, or sunny tomorrow. Right, and our probabilities, you can see that they add up to 1 across each row. All right, so these are not probability vectors the way that the way that we would like them to be, because they're given as row vectors. We need them as column vectors. All right, so all right. So we have to make an adjustment. Now, I'll read the rest of the question before I do that. If the Weather Channel says there's a 30% chance today will be cloudy, 50% chance that it'll be rainy, and 20% chance it'll be sunny, what does this say about the chance that tomorrow will be sunny? What about 4 days from today? So it doesn't say and so on, but you know, we can at least investigate that also. All right, so I'm going to make my probability matrix, again, based off of these parameters. So the first one is going to be 0.4, 0.4, 0.2. And so we're getting the transpose here. So 0.5, 0.4, 0.1, and then 0.3, 0.2, 0.5. All right, so it's still cloudy, rainy, and sunny in that order. It's just a question of what is referring to what. You know, so that first column is really saying, if it is cloudy today, these are the probabilities that it will be cloudy tomorrow. 0.4, 0.4, 0.2, right? Which I think would make somewhat a little bit of sense. If it's cloudy, like literally today, are you expecting, I mean, if, without any other information, you expecting a bright sunny day tomorrow based on what you perceive outside? Well, probably not. All right, bright sunny day is probably the last thing I would expect. The other possibilities are more likely. Same thing with rainy, sunny, you know, like if it's sunny today, yeah, it could be these other things, but my first thought would be like, why wouldn't tomorrow be any different? You know, unless there's a system moving in. But that's where the probabilities are coming from, because it's not just left to our own perception, hopes, and all that stuff. All right, so there's a 30% chance that today will be cloudy. So that's our initial vector. Rainy is 0.5, and the other 20% would be sunny. So the same structure, all right? So now we go to our Markov program. Oh, actually, that's not true. We go to our matrix editor, and we type in this information. And then we're going to type in a vector, the initial state vector. All right, so quit out of here. We need a 3x1 point 3.5.2. All right. So if you remember from last class, carrying out this process was, hey, it's still better than doing it by hand, but I will even follow that up by saying that this is generally not a topic taught in a class where you have to do stuff by hand, right? Because it's too cumbersome, all right? So you go to Program, select Markov, run that, and it'll give you your first product. Now it says, what does this say about the chances of that tomorrow will be sunny? All right, so probability tomorrow is sunny. Ooh, connection to prob and stat. Interesting. 0.21. All right, because it's only the last entry in the matrix that they're asking about. All right, that bottom number, that 1, is the number of iterations. All right, so we got a counter. All right, the 0th iteration was your initial state. That was the 0.3, 0.5, 0.2. So my second iteration, I need to get out to the 4th iteration, 4 days from today. So 3rd and 4th. So probability, sunny, 4 days later. Approximately 0.23, I'll just say 0.234. All right. So that's all the question's asking, but we could find, again, what we call a steady state vector, which would be if this progression were to continue repeatedly, what would the probability of a sunny day level off at? All right, so keep hitting enter until you perceive no change in...
This is in the program?
What's that?
This is in the program?
Yeah, the Markov program. All right, so as you keep hitting enter, you can see that it's, I mean, if you're looking for a rounded value, we've already gotten it. It's leveling off at about 0.235, right? So I can keep hitting enter, and get a more exact decimal, but it doesn't seem like that's really necessary. And in fact, and this is still a whole lot easier than what we were doing last time, it takes up until the 26th iteration before we get repetition, which means that it would take 25 days to get to our steady state vector, all right? And that's only for sunny, all right? Because I'm still not precisely the same for cloudy and rainy. All right, well, actually, I'm good on rainy, I'm not there for cloudy. All right, so I'd have to go a little bit further in order to get the other ones.
Whereas our version of the calculator levels off after 20 days and it gives you a round fractional.
Oh, okay.
As soon as it can get the round fractional, I guess it.
And then it stops because it's clean. Right, okay, so that's the drawback to mine. But, so, at least it's nicer for, I'd rather it be that way than, you know, because if I'm the only one that has a good one, then that kind of sucks. Right, so, but yeah, so we answered the question here, and, you know, it would question, I mean, you would consider what would be the benefit of finding a steady state vector with this scenario. Well, you start getting 20 to 30 days down the line. Well, think about what the weather was 20 to 30 days ago. I would actually amend that to say, think about what the climate was 20 to 30 days ago. It was a different world 30 days ago. I mean, we were talking about 70 to 80 degree temperatures. Now we're talking about like sub-freezing, all right? So, and we're not even into winter yet, all right? So this information here, these probabilities, they have an expiration date. But there are some situations that don't have an expiration date, like you're applying the concepts in industry where you're talking about money, currency exchange and things like that, where you could take information and apply it in the long run, right? So this is not necessarily one of those situations where you do that, but you know, if you're thinking about a probability related game, like a game of chance, where the events are independent. So like spinning a roulette wheel. You spin a roulette wheel and you place the same bet every single time. The probabilities are never going to change. The amount of money that you're placing will never change. Using a Markov chain, you could figure out what the long-term probabilities would be for playing this game. Right now, I will caution you by saying that if you're playing the game of roulette, long-term, you got bigger fish to fry than your grade in linear algebra, but there is applications to it. So if you're thinking along those lines, it's probably a good way to be going. Question?
Yeah, Professor, where'd you get the 0.3, 0.5
In the scenario here, it says 30% chance, 50% chance, and 20% chance. Yeah, it's always going to be given in the framework of the problem. All right, no problem.